Welcome to this session on hole cleaning, which forms submodule 2 of 3 in our training. In this module, we will examine the mechanisms, fluid properties, and operational strategies that impact effective hole cleaning. By the end, you should be able to optimize drilling efficiency through proper understanding of flow regimes, fluid design, and hydraulic practices. In this module, our focus is on the fundamental elements that govern hole cleaning performance. Hole cleaning is essential for safe and efficient drilling, as ineffective removal of cuttings can result in stuck pipe, excessive torque and drag, or wellbore instability. We will begin by reviewing flow regimes, exploring the difference between laminar, turbulent, and plug flow and how each influences cuttings transport. We will then evaluate velocity profiles in the annulus, considering the role of fluid rheology and borehole inclination. Next, we will study the relationship between cleaning rate and hole inclination, referencing findings from Ocrogini's SPE paper on mud cuttings transport in directional well drilling. This will allow us to understand how well trajectory impacts hole cleaning efficiency, particularly in deviated or horizontal wells. We will then move into drilling fluid properties, including density, rheological characteristics, filtration, solids content, and chemical composition, all critical to designing a fluid system capable of effective cuttings transport. Finally, we will consider optimization strategies such as adjusting annular velocity, maximizing hydraulic horsepower, and optimizing nozzle velocities. We will conclude with a design approach, looking at annular velocity and mud weight, tying all concepts together. By the end of this session, you will have both theoretical and practical insight into how to manage hole cleaning for efficient drilling operations. Okay, let's do a quick recap from the first submodule on the 3 primary flow regimes: turbulent, laminar, and plug flow. Turbulent flow is characterized by a chaotic velocity profile. While it enhances cuttings transport efficiency, it also creates challenges such as borehole wall erosion, high pressure drops, and elevated equivalent circulating density ECD. These effects can stress the formation and increase the risk of lost circulation. Laminar flow is more orderly and predictable. Fluid velocity is highest at the center of the wellbore and decreases toward the borehole wall, where there is virtually no movement. While this minimizes erosion, it significantly reduces hole cleaning efficiency, especially in deviated wells. Plug flow describes conditions where most of the drilling fluid moves at nearly the same velocity. Although it may provide uniform transport, fluid velocity at the borehole wall remains stagnant, limiting effective cuttings removal. Understanding these regimes is critical. In vertical wells, laminar flow may suffice, but in deviated or horizontal wells, turbulent flow is generally preferable to prevent cuttings accumulation. However, excessive turbulence may lead to erosion and higher operational costs. Hence, drilling engineers must balance rheology, pump rates, and annular geometry to achieve efficient cuttings transport while managing risks. Look at the flow regime velocity profiles. The left-hand diagram illustrates the different flow regimes. In laminar flow, velocity is parabolic with zero velocity at the wall and maximum velocity at the center. In turbulent flow, the profile is flatter, showing more uniform velocities across the borehole. Plug flow shows an almost square profile, where most of the fluid moves at nearly the same rate. The right-hand diagram presents a plot of velocity versus pressure drop, PSI, with laminar and turbulent flow regimes annotated. It demonstrates how flow transitions from laminar to turbulent as velocity and Reynolds number increase. What this tells us is that there is a trade-off between flow efficiency and energy cost. Laminar flow requires less pump pressure but is poor for hole cleaning. Turbulent flow improves cuttings transport but increases pressure drop and ECD. The picture in this slide shows a graph comparing laminar and turbulent flow velocity distributions across the borehole cross-section. This is similar message to the previous slide. In laminar flow, velocity follows a parabolic distribution. The fluid at the borehole wall has zero velocity due to friction, while velocity increases toward the center line, peaking at the core. This means cuttings along the borehole wall tend to settle, reducing cleaning efficiency. In turbulent flow, the velocity distribution is flatter. diameter. Near the borehole wall, fluid velocities are higher compared to laminar conditions, which enhances the suspension and transport of cuttings. This explains why turbulent flow is often preferred in directional and horizontal drilling operations. The graph emphasizes the impact of flow regime on cuttings transport. In laminar flow, stagnant regions allow cuttings beds to form, particularly in high-angle wells. Turbulent flow, by contrast, reduces stagnant zones and improves transport efficiency. However, engineers must manage turbulence carefully to avoid excessive ECD and formation damage. The goal is not always full turbulence, but controlled rheology and pump rates that provide optimal annular velocity while staying within operational pressure limits. The graph shown here is an excerpt from Okrajini et al. 1988, showing cleaning rate as a function of hole inclination under laminar and turbulent conditions. The graph plots cleaning rate, pounds per second, on the y-axis against well inclination, degrees, on the x-axis. Two distinct trends are shown. In laminar flow, cleaning rate declines significantly as inclination increases. This occurs because in inclined and horizontal wells, gravity causes cuttings to settle on the low side of the hole, and laminar flow lacks the velocity near the borehole wall to suspend and transport them. In turbulent flow, cleaning efficiency is far less sensitive to inclination. The higher energy and velocity distribution in turbulent regimes lift cuttings effectively, even in deviated well bores. This highlights a critical operational principle. In vertical wells, laminar flow may achieve adequate cleaning, but as deviation increases beyond approximately 30 to 40 degrees, turbulent flow becomes essential. For high-angle and horizontal wells, turbulent or pseudo-turbulent flow regimes should be targeted to avoid cuttings bed accumulation. This reinforces the importance of designing mud rheology and pump rates to transition into turbulent flow in challenging trajectories. Looking at the key drilling fluid properties affecting hole cleaning, the first property is density. This provides hydrostatic pressure to control formation fluids, but must be balanced to avoid excessive ECD and cutting settlement. A density that is too high can worsen sag and increase torque. Second is rheological flow properties. These govern the fluid's carrying capacity. High viscosity enhances suspension of cuttings, but can increase pressure losses. Optimal rheology is crucial for transporting cuttings without requiring excessive pump energy. Third is filtration characteristics. These control the invasion of fluid into formations. Poor filtration can lead to filter cake buildup, differential sticking, and poor hole cleaning. Fourth is the solid content and size distribution. Excessive or poorly graded solids increase fluid density and viscosity, reducing cleaning efficiency. Proper solids control equipment is necessary to maintain desirable levels. Fifth is chemical composition. This impacts the stability of clay formations and reactivity with drilled cuttings. Inhibitive muds help prevent the dispersion of shale cuttings, which would otherwise complicate transport. Engineers must evaluate these parameters holistically. Effective hole cleaning is not achieved by focusing solely on velocity. The fluid system must be engineered with a balanced density, optimized rheology, proper solids management, and appropriate chemical treatments to ensure stable and efficient transport of cuttings. When looking at fluid velocity, there are some important optimization parameters which improve hole cleaning. The first is annular velocity. This is the single most critical factor in cutting transport. Sufficient annular velocity is needed to suspend and carry cuttings to the surface. However, higher velocities increase ECD, which may fracture formations if not managed. Next is hydraulic horsepower or jet impact force. At the bit, sufficient hydraulic horsepower ensures effective bottom hole cleaning and cuttings break up. Jet impact force helps scour cuttings from the borehole bottom and minimizes bit balling. Finally, we have the nozzle velocities. Proper nozzle sizing ensures hydraulic energy is efficiently converted into cleaning force. Incorrect nozzle selection can reduce hydraulic efficiency and limit the effectiveness of hole cleaning. Optimization requires balancing these parameters against operational constraints such as pump pressure, mud properties, and rig capabilities. The goal is to maximize cutting transport efficiency while minimizing risks of stuck pipe, excessive torque and drag, or wellbore instability. Practical optimization involves real-time monitoring of cuttings returns, annular pressure, and pump performance to fine-tune flow rates and fluid properties. Key goals of hole cleaning optimization. First, cuttings distribution in the annulus. Our aim is to achieve a uniform profile with no cutting beds forming on the low side of the hole. In horizontal shale gas wells, for example, if the annular velocity drops too low, cuttings quickly accumulate, leading to a stuck pipe. Drill string rotation can help by stirring the fluid and redistributing cuttings. Next, a stable wellbore with minimal hydraulics. Excessive annular velocity can erode the borehole, while high ECD can exceed the fracture gradient. In depleted sandstone formations, this often leads to severe lost circulation. By applying only the necessary hydraulics, we keep the wellbore intact and minimize instability. Third, bit performance. Clean bottom hole conditions improve penetration rates. In deep water drilling, where bit trips are expensive, maintaining good jet impact force ensures the bit stays cool and free of balling, extending its life and reducing costly non-productive time. Finally, surface horsepower utilization. The pump's horsepower must be directed toward useful cleaning energy, not wasted in frictional losses. For example, in long ERD wells, efficient use of surface horsepower makes the difference between steady hole cleaning and excessive drag. Together, these goals create a balance between efficient cuttings, transport, wellbore stability, and drilling performance. In the design approach to achieving effective hole cleaning, the first point is to optimize equipment use. This involves maximizing the use of available rig pumps, nozzles, and drill string rotation to optimize fluid circulation. Even with limited horsepower, equipment settings can be adjusted to maximize efficiency without overloading the system. The third point emphasizes hole conditions. Apart from mud properties and inclination, annular velocity is the single most crucial factor for hole cleaning. However, too high an annular velocity can erode the borehole wall, leading to instability, higher ECD, and even loss of directional control. The key is to determine the lowest annular velocity that will still clean the hole. This value varies depending on hole size, inclination, and formation type. Once identified, maintaining this velocity within the safe mud weight window ensures efficient cuttings transport while avoiding formation damage. Here we see the formula for annular velocity, or AV, which tells us the average upward speed of the drilling fluid in the annular space. Examining the terms, Q represents the flow rate measured in gallons per minute. As you would expect, the faster you pump, the higher the annular velocity. dH is the hole diameter in inches. dP is the diameter of the drill pipe or bottom hole assembly component, also in inches. The difference between these two values gives us the annular cross-sectional area, the space through which the mud flows. Now, what does this mean in practice? If the annulus is large, velocity will be lower for the same flow rate. If the annulus is tighter, velocity increases. From a hole cleaning standpoint, annular velocity is critical. If it's too low, cuttings will settle out, especially in high angle and horizontal wells. But if it's too high, we risk excessive equivalent circulating density, borehole erosion, and wellbore instability. The key is balance, finding the minimum velocity that effectively transports cuttings while staying within safe hydraulic limits. A common issue that can happen is that the hole enlarges due to wellbore stability, which causes the annular velocity to drop, resulting in poor hole cleaning. This means bigger cutting beds and a greater risk of stuck pipe. The graph shown here is the relationship between yield point and transport ratio when comparing different mud weights. The transport ratio is the hole cleaning efficiency. The primary purpose of mud weight is to provide hydrostatic balance and prevent influxes. However, mud weight also influences cuttings transport indirectly. What we can see from the graph is the impact on cuttings slip velocity. Higher mud density increases buoyancy, which reduces the effective weight of cuttings, making them easier to lift. This improves hole cleaning efficiency in vertical wells. The limitations are that excessive mud weight increases ECD, which can fracture formations, cause lost circulation, and reduce hole stability. It may also worsen sag and increase solids loading. Mud weight must be optimized in combination with annular velocity and rheology. While higher mud weight can improve suspension, it is not a substitute for sufficient flow velocity. In directional wells, annular velocity remains the dominant factor, while mud weight plays a supportive role. In this submodule, we looked at the key factors that influence efficient cuttings, transport, and wellbore stability during drilling. We began by examining flow regimes, laminar, turbulent, and plug flow, and their impact on velocity distribution and cutting suspension. Graphical comparisons demonstrated that turbulent flow, although more energy intensive, delivers significantly superior cleaning performance, particularly in deviated and horizontal wells. We then explored the relationship between hole inclination and cleaning rate, referencing Occhigini et al. 1988, which highlights the decline in efficiency under laminar flow as deviation increases. This set the foundation for analyzing drilling fluid properties such as density, rheology, filtration, solids content, and chemical composition, all of which are critical in controlling hole cleaning dynamics. Next, we discussed optimization parameters, including annular velocity, hydraulic horsepower, and nozzle velocities, alongside operational goals, uniform cuttings distribution, stable wellbore hydraulics, efficient bit performance, and effective use of surface horsepower. The design approach emphasized the balance between pump horsepower, annular velocity, and safe drilling margins. The key takeaway is that hole cleaning is not about maximizing flow indiscriminately, but about carefully engineering fluid properties and hydraulics to achieve the minimum effective annular velocity that ensures safe, efficient drilling operations. This ends submodule 2 of 3 on hole cleaning. We have examined flow regimes, fluid properties, optimization strategies, and design principles for efficient cuttings transport. Please proceed to the quiz. Thank you.